2 minutes. All right, 12:30. Yeah, you're a light one today, yes. Lord, thank you for bringing us together this afternoon. Thank you for the promise this coming weekend. Pray that you would help us all to accomplish the things that we set out to do, to set aside some time for ourselves this weekend, refresh, recharge, and come back next week ready to go. In your name we pray. Amen. All right, so today we're going to continue on with what we were talking about last class, right? And so let's see, was there anything on here? Let me pull this up. One sec, sorry, should have been prepared for this. It's not like this happens every class where I have to do this. Okay, so equations, everything, rotation. Well, we've done a lot of things in the last 6 weeks, so going over everything would literally take the other half of the semester. Right, so it's going to be tough. Equations, right? Equations. What equations are we talking about? Right? So far we've been talking about rigid body kinematics, right? Rigid body kinematics do also follow the rigid body kinematic equations, right? Those kinematic equations, when we have rotation about a fixed axis, are the same as the kinematic equations that we've been using for translation of a particle. Instead of x, we have theta. Instead of v, we have omega. And instead of a, we have alpha, right? Otherwise, they are the same form. Right? We're just using angular position, angular velocity, and angular acceleration as our variables. Rotation. I'm going to need a little context. Maybe it was the rotation equations, maybe. I don't know. I need a little more context. Rotation is a big topic. We're going to go over some more of this stuff today, right? We're going to do an actual problem or something in general planar motion, right? What we spent most of our time talking about last class was rotation about a fixed axis, right? So if you have something rotating about a fixed axis, we use these nice kinematic equations. Right? We can use our nice Can's kinematic equations. If we don't, right, then we have to consider something else. It's a good segue into what's going to come up next, right? So you guys don't have anything due for a couple weeks, so it's fine. Homework 4 and chapter 16 months on for you on the first. All right, so what happens if things are not just rotating or not just translating, but doing some combination of the two? This is what we call general plane motion. And what we're trying to do is determine how this system works. Now, I think if you look at this system, right, what's going to happen? B is going to move down and A is going to move to the right, right? And so as this moves down and to the right, this bar is going to end up straightening out, right? And if you were to move it the other way, the bar would straighten out vertically, right? So this bar is rotating, but the center of gravity, right? If we track the center of gravity here, this center of gravity is going to be doing what? Well, it's going to be dropping and moving to the right, right? Because this is going to rotate out. And so eventually you'll have a bar that's flat like this, right? And the center of gravity is here. Okay, so this system is both rotating and translating if we're talking about any particular point on our bar, right? And that's the thing about rigid bodies, right? Because they are rigid bodies, we know that if one point moves, all the other ones have to move in a similar fashion, right? So if this point slides out this way, well, all of this is going to have to slide this way, but this side's going down, so this also has to move down, right? The net motion is a rotation and a translation of our bar and slider system. It is both translating and rotating. So how do we deal with that? We deal with that by breaking it down. We know the velocity at point A, right? We know the velocity at point A. So we're going to assume the entire bar is moving with some velocity v sub A, right? So this bar is just going to end up in this position, right, at some point. Or imagine that this is in time, right? So this has moved to this position, right? It started there and we slid it over, right? Now A is in the final spot it's going to be, right? A is slid all the way over. And now we have to figure out how much do we rotate? Right? How much does this bar rotate because B has to move downward? And how do we do that? We hold point A in place, right? Because point A has gotten to where it needs to go. And we're going to rotate everything about point A. We know that VB goes downward. So we know that the relative velocity of point B with respect to point A has to move in this manner. Has to move down into the left. And that's what we draw here. And that moves perpendicular to the bar, right? So we can figure out some things here, right? So assuming that the velocity of A is known, we want to determine the velocity of B and the angular velocity omega in terms of VA, L, and theta, right? So we want two things. We want the velocity of point B and we want omega. I want to know how fast is point B moving and I want to know how fast am I rotating. Right? Those are the two things I want to, we need two things, two equations, right? So we can do some trig if we use this triangle here. And we're going to do a couple of examples in a minute, right? We didn't do any examples of general plane motion yet. We'll do a couple, and you can start to see how some of this will play out, because I think that's going to be exceptionally helpful here. Right, so what is this, right? Well, this is just based off of this velocity triangle. How do we get this? Well, again, when you look here, right? I know that the velocity of B is going this way, and I know that the velocity of A is going this way. So the relative velocity is the difference between those two velocity vectors, right? V of B with respect to A, the equation is given here for VB, but right, this comes from V of B with respect to A is equal to VB minus VA. One minus the other. Okay? One minus the other. Once we know that, we can, algebra it to get into that form, right? If we look at this diagram, we can use trig identities to get a relationship between v sub a and vb with respect to the a. We know that vb with respect to a has to equal L times omega. Why? Because we know it acts perpendicular to that point, right? Why do we know that? Because that's how tangential velocities work, right? That's how tangential velocities work. Right? So this is a little bit abstract, right? And then we can do the same thing in the opposite way, right? We can do the same thing, but we'd say, you know what? This time I know B and I want to find A. We do the same thing. But what happens? Well, instead, we're going to have B in its final position, right? So everything's going to move down. The whole system drops. B is now at some point here, right? And we want to figure out how much A has moved, right? That's a rotation about point B. Notice before this was rotating this way in our previous diagram, right? Which is the same direction that B is rotating, right? It doesn't change the direction that it's rotating, right? It rotates in the same manner. The other thing that's different is our triangle, right? Our triangle here is slightly different because the velocity of A with respect to B is BA minus BB, so it's in the opposite direction of BB with respect to A, right? It's going to have the same magnitude, but the opposite direction. So you get equations, right? All right, why don't we work through them, right? So this is a gear inside a gear that rotates. So the two things rotate, and then there's a rack here, right? So the double gear rolls on a stationary lower rack. The lower rack is stationary, right? The lower rack is not moving. The velocity of the center of this, imagine this is a wheel, right? Of this gear assembly, right? This whole thing is translating down the track, with a velocity of 1.2 meters per second. It's also rotating, right? But we can imagine, if you will, right? You can pick this up, slide it, and put it back down, right? We would just translate it without doing any rotation. So let's talk about that, right? In a second. We want to find the angular velocity of the gear and the velocity of the upper rack R and point D on the gear. Okay? So there's a few things that we want to do. So let's draw our diagram, right? Let me get rid of that for a second. All right, so here's my rack. That's my upper rack. Here's my inside gear. My outside gear, the top got cut off by the top of the screen, but that's not really super important. And here's my bottom rack. This is R2, this is R1. We have point C down here, point D over here, point B. So this is R. And point A is the center, right? We know that there's some velocity V sub A here. And we're going to have our coordinate axes. That's important. Remember, so we have X, Y, positive counterclockwise rotation. I think we've got everything that we need here, right? What do we want to find? I want to find omega for the gear. That's part A. And part B, the velocity of R and the velocity of point D. So I think, right, we talked a little bit about this, right? This is rotating and it is translating, right? So that screams to us that we need to use general plane motion. In general plane motion, what do we do? Well, we just talked about it, right? We are going to translate everything by a specific known velocity, and then we're going to rotate it, right? So we know velocity, we know how fast the entire gear assembly is moving, right? And we know that that's moving with v sub a. Now imagine, I said before, right? Imagine I'm going to pick this up, lift it off the track, and I'm going to carry it with v sub a and put it down, right? It moves some distance. We'll say that over a certain amount of time, right, we will have moved by some distance x sub a. Promise this is going somewhere. Let's see. How do we, what's that?
The gears like that, right? Like they're both moving same.
Yeah, they'll both be moving at the same velocity, correct. And they'll both have the same velocity translationally, but they should also have the same rotational velocity, right? Because they're rotating about the same fixed point. So how do I figure out this distance, right? Because this, I want to know how far, right? We're doing kinematics. Part of this is going to be figuring out how far we move. How do I figure out that x, right? Well, let me ask you this. How far should this, if you had a wheel, right? If you had a wheel and you rotated it one revolution of that wheel, how far would it be? How far would it be? The circumference, exactly, right? So if this rotates one time, we should move the circumference of that outer gear, right? Okay. So x sub a is equal to 2 pi r, right? So if that's true, that means that, right, the center of gravity of this moves by the circumference, 2 pi, specifically r1, right? Specifically r1. So I can create this ratio, right? The distance that I've traveled over the circumference of the circle has to equal the angle that I have traveled through, right? Divided by 360 degrees. All right. So what is actually going on, right? What does this mean? What does this mean? The linear distance is some portion of the circumference, right? The linear distance, x sub a, is some portion of the circumference. What does this distance depend on? Depends upon how many revolutions the wheel does, right? So, for example, if x sub a is equal to 2 pi r, right, we will have done one revolution, which means that theta would be equal to 2 pi, right? So we're trying to figure out how much of the circle have we rotated through, right? How many revolutions have we done? That's what this equation does. It tells us what percentage of revolution, or how many revolutions have we done? And what is the linear distance that you can expect to get out of that based off of it? Now, it's going somewhere, right? This is actually negative because of reasons, because of direction reasons, right? So I can simplify this, right? I can multiply through by 2 pi, right? If I multiply both sides by 2 pi, this and this go away. And it turns out that x sub a is equal to negative r1 times theta. Now, why is this important? We don't need to know anything about position, right? But we were asked to find omega, which is a velocity. How would I get the velocity of that point A? An equation for the velocity of point A from the equation that I just wrote. How do we go from x to v? Derivative, exactly. So if I take the time derivative, well, theta is the position of the angular position with respect to time, right? That becomes omega. I know VA and I know R. So I can plug and shove to get omega, right? VA was what? VA was 1.2 meters per second. R1 was and so sorry, this is R1. Let's write down VA 1.2 meters per second. R1 is equal to 0.15 meters and R2 is equal to 0.1 meters. Right, so if I rearrange this, omega is equal to VA over negative R1, which is equal to 1.2 over 0.15 is equal to negative 8 radians per second. What does that mean? It means that omega is going this way, at negative 8 radians, at 8 radians. That makes sense, right? If something was rolling, and if we had a wheel, we'll go back to the wheel. We're rolling our wheel from left to right here, right, on the ground. It's going to rotate clockwise, right? Rotate clockwise. That's how we gain that lateral position. All right, so part A is done, right? Part A is done. We need to do a little bit of math magic, right? It's done. Yeah, exactly.
Does it matter if for the omega, whether you use R1 or R2?
So, does it matter if you use R1 or R2? The issue is that you can use R2, but R2 has that rack that's moving at the top, which is also going to affect the velocity at that point. So yes, at the end of the day, what we'll find, right, is that you can, but it's a little bit more involved. The reason why it works nicely with the ground one is because we know that's not moving. The top one is also moving, so it's a relative velocity thing, right? So VA and VR are moving at different, possibly in different directions. So the total velocity seen at point B is different, right? Any other questions on part A? No? Part B. We need to find V sub R and V sub D. Okay. These are rigid bodies, right? We can figure out the velocity of any point on a rigid body if we know the velocity of another point and how we're moving relative to that point. Okay. In general, that's written like this. I have some velocity P, which is equal to VA plus V of P with respect to A, right? This mask is itchy, man. Itchy. Switch the turbines. V of P with respect. So in our case, right, we need to find the velocity at point R and the velocity of point D. We can use this equation. Right? So we're going to use this equation in a second. First, let's start with point R, right? Let's start with the rack, the velocity of the rack, right? So potentially, like, let's think about this, right? This gear is rotating clockwise, right? If this rotates clockwise, which way should the rack be moving, do you think? To the right or to the left? To the right. Spin this way, it's gonna keep think about it this way, right? If there's a flag at the top, you would smack it and it would move a little bit forward every time, right? So as this rotates, that rack should be moving to the right. So we can say, hey, well, this is probably going to have some velocity v sub r. When we were doing those cable problems and those conveyor belt problems the other day, and I asked you, what's the velocity at point B? Right? What's the velocity of point B if I know the velocity of r? It's the same, right? It's the same deal as our conveyor belt problem, right? R is a rigid body. So at this moment in time, if we were to take a snapshot of this and track the velocity of every single point in this rack, they would all be v sub r, right? All of them, including the one that touches point B, which means that the velocity at point B also has to be equal to v sub r. Okay? That's important. Why? Well, because we can calculate v sub. Come on, give me this eraser. Thank you. We can say v sub r is equal to v sub b is equal. Well, I know the velocity of point A, right? That's a point on the rigid body that we were given. Plus v of b with respect to A. Okay. We can rewrite this again based on the equations we set up last class. What's the relative velocity of point B with respect to point A? Well, we wrote this last time. Omega about the z-axis, okay, cross the relative position of B with respect to A. So we're going to have to do a cross product. So we're going to have to do a cross product. Right? Because these are going to be vector equations. Just have my IJK circle there. It's cool. Talk about it in this. So these are vector equations, right? I can rewrite this. Well, v sub A was given as 1.2 meters per second in the I direction. And that's going to add to my cross product here. I know omega, right? It was -8 radians per second. What is the relative position of point B with respect to point A? Good question. If I'm at point A and I'm trying to get to point B, how do I get there? If you had to give me directions, what would you say? I'm at A and I want to go to B. How would you get there? How far would you have to go? R2. Is it R2 to the right, to the left? Yeah, so it's R2 straight up. That's R2 in the positive J direction, right? R2 in the Y direction, positive Y. So we have a vector, right? So this is going to be 0, 0.1, which was R2, 0. Okay. So then we can take our cross product here, right? I'm going to switch over to the board because this is going to be easier to kind of explain there. I apologize that if you're watching this on repeat, you're not going to see it, but 6-1. All right, so here's my cross product, right? I, J, K. 0, 0 minus 8, 0.1, 0. Okay. Okay. So what do? First thing we need is the I direction, right? We cover up the first column in the top row. What are we left with? 0, 0, 0.1, and -8. Right? So we're taking a cross product, we cover the I column, we cover the top row, and we're left with this. What's this? Well, this is 0 times 0 minus 0.1 times -8. That whole thing is in the I direction. How do I know it's in the I direction? Because we're doing it in the I direction, but if you didn't remember that, J cross K, remember? I drew it on the slide here. J cross K gives me positive I. Okay. Okay. What about the J direction? Cover up the middle one. What am I left with? If I cover up this middle column in this top row, what do I have? Right? We got these right at the corners. What should my cross product be for those? 0, right? 0 times 0 minus 0 times 0. Right? So write that as 0 times 0 minus 0 times -8, which is 0. And that's going to be in the J, right? Except that it's I cross K. I cross K goes in the opposite direction of my circle, so that makes it negative. So we're going to subtract it. Not that it matters for this one, but later, that term might not be 0, and it could matter. What about K? I'm going to cover up my last column. What am I left with here for the K one? What am I left with for K? There we go. 0 again. 0 times 0 or 0 times 0.1 minus 0 times 0. J cross K. Positive 1. Sorry. I cross J. Positive K. We can cover it up. Okay. We have I cross J. Positive K. We would add these. Right. So we're left with what here? Right. We're left with what? Well, we're left with positive 0.8. Right. That's what's left here. So when we take this, this is equal to 1.2 I plus 0.8 I. 2.0 in the I meters per second. That's the velocity of point R. The velocity of point. All of these types of problems, when we're doing rigid body kinematics, are going to come down to us doing not always a cross product, but for us using, they're going to come down to us using the relative velocity equations. Right? We also need to find the velocity of point D, right? So velocity of point D, we're going to use this equation, v of d with respect to, which we'll make the inference that this is just going to be this equation, right? It's just going to look like the same thing, but we're going to do it for part. For point D, let's look back here. What direction is the velocity at point D? If you were at point D, what way would you be moving at this instant in time? This is rotating, right? It's rotating clockwise. I get to the point D, right? So if I'm at point D, imagine point D is taking the path of this circle around and around, right? It's rotating clockwise. Once I get to the left-hand side, how is this moving? Which way is the velocity?
It's on the bottom.
Talk about point D, right? All the way on the left-hand side here.
That makes sense. Um,
Straight up. Something straight up. All right. Well, if that's straight up, then let's draw that as. So we would expect to get some sort of J component here. All right. Remember, the relative velocity, or not the relative, I'm sorry. Yeah, the relative velocity of point D with respect to the center, right, with respect to point A, is just omega cross R D with respect to A. What is R of D with respect to A? If I was at point A, give me directions on how to get to point D. I want magnitude and I want direction. You have that. Remember, that was R of B with respect to A. So how do I get to D? The distance of R1, yeah. Give me the direction. Go up. Right, so you're going to move like this, right? This is going to be R of D with respect to A. R of D with respect to A is just R1 in the negative I direction, right? Moving to the left, in the negative X. All right, so we can construct this now, right? We can say this is 1.2 I plus the cross product with the same omega, and omega hasn't changed. But we've got R1 is negative I direction, 0. Okay. Go over to the board again. Good. Cover it up. Cover it up. What am I left with if I do that cross product? What am I left with if I do this cross product? I cover it and cover it. What do I have? Zero. Yeah, 0 times 0 minus 0 times negative 8 in the I direction because of J cross K. All right, what about the next term? What do I do if I cover the middle and the top? Using my corners, what do I get? Negative 1.2 here, right? 0 minus 1.2. But your I cross K. I cross K is a negative J. The other one's going to be 0, right? How can I tell? Well, you got 3 zeros. Whenever you see a bunch of zeros like that, it's always good for business, right? Because then we have to do less cross product, right? So we're left with 1.2 I plus 1.2 J meters per second, right? And this is the vector for velocity of D. And if you got this answer on a quiz and you left it like this, I would be very, very happy. And you would be happy because you would get all the points. When you're doing the homework, sometimes they want you to do the magnitude and the angle, right? And we'll talk about how to do that, but these are two equivalent ways of talking about this. Right? We already talked about what's happening physically, right? This is, if you're at point D, you are seeing a translation by VA, right? But also there's that tangential velocity that we thought, right? So we have a physical intuition about what the system is doing. So what if I wanted, do I have another slide here? Yes. All right, so we found that V sub D was equal to 1.2 I plus 1.2 J meters per second. But I want to do this in terms of the magnitude, right? And the magnitude is just the Pythagorean theorem, right? Because what is the magnitude? Remember, if I have V sub D in the x direction, V sub D in the y direction, this is the resultant of the two, right? We can use our Pythagorean theorem to figure out what is the, I'll get there, what is the magnitude, right? How strong is this? Guess what? You do this math, it's gonna be 1.7 meters per second. But then we need an angle, right? So how do we find the angle of the velocity? Well, I can take the tan inverse of my y over my x. And that's going to be 45 degrees. Remember, tan is opposite over adjacent, y over x, 45 degrees. Yeah. These, reporting this as a magnitude, right? Reporting this in this way is equivalent to reporting it as this vector. Those two things are the same. Those two things are the same. They're just different ways of giving the same information. Do you have any questions on this one? No? Yeah. Is it not going to play my video? There we go. So we're going to watch a video.
In this Easy Ed video lecture, we will see rigid bodies moving in a general plane motion and methods to solve bodies under general plane motion, which is relative velocity method and instantaneous center method. Any plane motion which does not fall under the category of rotation about fixed axis or translation motion can be put under the category of a general plane motion. A general plane motion is a combination of translation motion and rotation motion. Human movement usually consists of general motion rather than pure linear or angular motion.
Seriously, pay attention. This is important.
General plane motion is a sum of translation and rotation motion. To find the angular velocity of a body performing general plane motion, we use relative velocity method, which is one of the methods for analyzing a general plane motion. Consider a rod AB pin connected to slider A and B which moves in a fixed slot. Let slider B have a known velocity Vb to the right. Steps to find angular velocity omega AB of the general plane body AB. Step 1. Locate a point whose magnitude and direction is known. Here, magnitude and direction of point B is known. Step 2. Locate a point whose direction is known, that is point A. Step 3. Now, divide the motion of the body as a sum of translation and rotation motion. Translate the body with translating velocity, that is Vb, and rotate it about a fixed point B. Step 4. Write the relation for the relative linear velocity of a translating point. For point A, we will write the relation as shown. Step 5. Write the relation for the absolute velocity of the translation point. Simultaneously, draw the vector diagram of the same. From the relation, VAB can be found out, and when we substitute the value of VAB in relation for relative linear velocity, we get an angular velocity omega. Let's take an example and solve it by relative velocity method. The figure shows 3 bars, AB, BC and CD. Internally pin connected at B and C, and externally hinge supported at A and D. In the position shown, bar AB has a constant angular velocity of 6 radians per second anti-clockwise. Find the angular velocities of bars BC and CD for the instant shown. Here, rod AB performs rotation motion about A, rod CD performs rotation motion about D, and rod BC performs general plane motion. Consider rod AB. Rod AB rotates about a point A, so direction of velocity at point B would be perpendicular to the radial distance AB. Therefore, using relation between linear velocity and angular velocity, on substituting the values, we get velocity of Vb as 1.5 meters per second. Consider rod CD. Rod CD rotates about a point D, so the direction of velocity at point C would be perpendicular to the radial distance CD. Let beta be the angle made by VC with the vertical. From the geometry, the value of beta is 46.97 degree. Therefore, using relation between linear velocity and angular velocity, on substituting the values, we get equation 1. Consider general motion of rod BC. For general plane motion, we will use relative velocity method. Step 1. Locate the point whose magnitude and direction is known. Here, velocity of point B is known. Step 2. Locate a point whose direction is known, that is point C. Step 3. Now divide the motion of the body as sum of translation and rotation motion. Translate the body with the translating velocity, that is Vb, and rotate it about a fixed point B. Step 4. Write the relation for the absolute velocity of the translation point. Simultaneously, draw the vector diagram of the same. On solving the triangle, we get velocity at point C as 2.2 meters per second and relative velocity of C with respect to B as 1.61 meters per second. Step 5. Write the relation for the relative linear velocity of translating point. On substituting the value, we get an angular velocity of rod CB. Now, substituting the value of VC in equation 1, we get angular velocity of rod CD.
Seriously, pay attention. This is important.
Instantaneous center is defined as the point about which the general plane body rotates at the given instant. The instantaneous center of rotation lies at the intersection of the perpendicular to the velocity. Let us see steps to determine the instantaneous center. Consider the mechanism of a rod attached to a slider. We have the given velocity of VA and we have to find an angular velocity of rod AB at the given instant. Step 1. Locate a point whose magnitude and direction of velocity is known and another point whose direction of velocity is known. Step 2. Draw the perpendicular to the direction of velocities and extend them to intersect at a point. Call the point as I. Step 3. Point I is the center of rotation of the general plane body at the given instant. On using the relation V equals R omega, the angular velocity of rod AB can be found out. Once the angular velocity is known, we can find the position of another velocity. Let us solve a problem on instantaneous center method. The figure shows collar B, which moves up with a constant velocity of 3 meters per second. The collar is pinned to rod AB and A slide freely against a 45-degree sloping ground. For this instant, determine the angular velocity of the rod and velocity of end A of the rod. The system consists of two bodies in motion. Rod AB performs a general plane motion and collar B performs a rectilinear translation motion. Considering a general plane motion of rod AB, using instantaneous center method, step 1. We know velocity at point B, that is 3 meters per second. Also, the direction of velocity of point B and direction of velocity at point A. Step 2. Draw the perpendicular to the direction of velocity at point A and B. Let the point of intersection be I. Step 3. From the geometry, the radial length can be found out using the sine rule to solve triangle ABI. On evaluating, we get the radial distance. Step 4. Use the relation between the linear velocity and an angular velocity at point B. On substituting the values, we get angular velocity of rod AB as 1.06 radians per second. Now, use the relation between linear velocity and an angular velocity at point A. On substituting the values, we get the velocity at point A as 2.3 meters per second. Let's take a quick overview of this Easy Ed video lecture. In this video, we have seen that any plane motion which does not fall under the category of rotation about fixed axis or translation motion can be put under the category of general plane motion. A general plane motion is a combination of translation motion and rotation motion. After which, we have seen the relative velocity method, which is used to determine the angular velocity of a body performing general plane motion, and steps to determine the angular velocity of the rod by taking an example. Instantaneous center is defined as the point about which the general plane body rotates at the given instant. The instantaneous center of rotation lies at the intersection of the perpendicular to the velocity. Finally, we have seen steps to determine angular velocity and position of velocity with instantaneous center method. So this is the overview of our video lecture.
All right, so there's a lot of stuff in there, and some of it that we're going to talk about, the instantaneous method, instantaneous center method. We're going to talk about that in a couple of minutes, right? But first, we're going to go through this using our relative velocity method again. All right, so there's a couple of things about this, right? So what do I have? I have a crank AB that has a constant clockwise angular velocity of 2,000 RPM. So the crank position shown determine the angular velocity of the connecting rod BD and the velocity of the piston P. Now there's a couple things here, right? And there's a couple of things that the guy didn't talk about in the video, right? But specifically, this is in a housing, right? This is piston in a housing. This piston cannot move up or down. It can only move left and right? Which simplifies this problem, right? Because I know that the velocity of point P, the velocity of the piston, has to be horizontal in one direction or the other. Similarly, because point P is rigidly attached to point D, right? Point D is a point on the piston. It's going to have the same velocity as the piston, right? Okay. So let's run through this. How do we do this, right? So what's happening? Remember, this is AB is rotating clockwise, right? So this link AB, right? That link is only spinning. It's going to spin around and around and around and around. As that spins, what happens? Well, we'll push the piston in and pull it out. Push it in and pull it out. Constantly forever, or until it breaks, one or the other. So let's draw. We're going to draw our diagram. All right, let's start with the link AB. Here's A, here's B. It's 3 inches long. That was a horrible place to put that. We'll try that. Let's try that one more time. Make it a little bit bigger. 3 inches, A and B. I know, right, I'm told that this has some omega. We'll call it omega AB. Right, we know what that is. We were told in the problem statement what that was. We'll talk about it in a second. Right, this part here is the ground, and this forms an angle of 40 degrees with the ground. In this moment, I will have a velocity of point B directed like this. How do I know that? Well, it has to be perpendicular to, right? So think of it this way, right? The whole thing is spinning. That point B, because it's spinning, point B has its own velocity, right? That's tangential to that circle that it's spinning on, right? If this was allowed to spin freely, this would form a circle of radius 3, right? And at this point, we have some velocity caused at point B caused by our rotation. Right? What is the rotational velocity? Well, we were told that omega AB was 2,000 RPM count in clockwise direction. So that's going to make it negative for us, right? Because we tend to use this coordinate system here, where we have X positive to the right, Y positive up, and that means you curve your fingers X into Y, positive Z is coming out of the board, so our curvature is positive counterclockwise. All right, so we've got this. I can convert this into radians per second, right? How would I do that? Well, RPM, let's just rewrite this as revs per minute times 1 minute for 60 seconds times 2 pi radians per revolution. Revolutions cancel, and I'm left with radians per second. So this gives me negative 209.74 radians per second. Okay. We're also going to need a little bit of geometry here. And so I'll try to draw this as best I can, as straight as I can. 40 degrees. This is V sub B. It makes 90-degree angle here. Right? So if I extend this upward and I make a flat line there, right, this would also be 40 degrees, right? Because it's still going to be 40 degrees from the horizontal no matter where we are. But then this angle in here, this is now alpha, okay? And what's alpha? Well, alpha is 180 degrees minus 90 minus 40. So it is 50 degrees. Where did that come from? Make the line by itself. I'll do it with this. If you were to measure the angle from here all the way to the other side, right, straight line, 180 degrees. I know how much this portion is, that's 40 degrees. I know how much this portion is, it's 90 degrees. Whatever's left has to be the remaining, right? It's 50 degrees. Okay. Great. Right. Why do we need that? We'll get there in 1 second. And it's confusing because I use alpha now for an angle. What if we need alpha for an acceleration? Well, we won't for this problem because we're looking solely for velocities and we're not talking about accelerations. Towards the end of class, we're going to stop using alpha to describe angles because we need alpha to be our angular acceleration, right? But for right now, we're okay. That's just an angle. Don't worry about it. So what's the first part? What do I need? I need to figure out what the velocity of point B is, right? Why? Why? Because remember what we're trying to do. We're trying to find, right, what are we trying to find? Trying to find the angular velocity of the connecting rod, BD. I need the angular velocity of this, and I need the velocity of the piston, right? I need two things. We're going to have to use general plane motion to describe the motion of BD, right? As this rotates, the point G is going to move translationally somewhere in space, but the entire bar itself is also going to be rotating, right? Okay. So if we need to figure out V sub B, if we looked at this, V sub B would be omega A B times R, which is 209.4. Sorry guys, I can't read my own writing. This is supposed to be 209.44 times 3 inches, which gives me 628.33 inches per second, which is angled at 50 degrees. If you wanted to, you could write this as X and Y components, right? You could. But we're not going to for right now. We're going to leave it like that for a second. Leave it like that for a second. All right, so far, any questions on how we find the velocity of point B? Is that making sense to everybody? Yeah. You have something that's rotating, just do omega times R to find out what the velocity of that point is, right? Okay. Let's do a little bit of geometry, right? Let's do a little geometry. Everybody loves geometry, right? Yeah. No, not really. Yeah, well, we're gonna do it anyway. Here's point A, here's point B, here's point D. Make sure our line goes up. Yep, we're good. I got this triangle, A, B, and D, right? I know right here that this is 40 degrees. I'm gonna call this angle in here beta. I'm gonna call this angle right here beta. I want to take it way back for this one. I'm gonna deep dive into your brain right now. I'm gonna pick out the choicest of trigonometric functions. We're gonna use the law of sines to figure out the angle beta. Can we use the law of sines? Sure we can, right? Why? Because I know this distance, 3 inches. I know this distance here is 8 inches. What does the law of sines says? Well, it says the sine of beta over 3 inches, right? Because this angle is across from this leg of the triangle. So it's the ratio of the sine of my angle divided by the length of the leg across from it is equal to the sine of 40 degrees over 8 inches. So beta is equal to 13.95 degrees. Why do we need that? Well, we are going to need that to figure out components of this velocity of the bar from D. We're going to need that later. Okay. So we find that angle. Great. What do we do now? I'm going to draw another diagram. All right. I'll draw another one. This time it's just going to be of the link BD. Okay. And so here's my link BD. Right. What do I know about it? Well, I know that velocity, another velocity of point B, right? And there's some angle with the horizontal here that's going to be 50 degrees. I know that at point D, I've got this angle here, and that's my angle beta that I just found, the 13.95 degrees. And in the final position, right, in its final form, this is going to do this, right? Point B is going to be moving down, and point D is going to be moving to the right, right? Because it's in the piston channel, right? So if I want to get to this motion, what can I do? Well, I have to take this and say that everything's translating by VB, right? And if you do that, you know that this is 50 degrees and this angle is 50 degrees, right? From the horizontal. All right, everybody's good with me so far, right? Remember what we're doing. When we have general plane motion, we break it into a translation plus a rotation. Our translation is going to be by VB because I know what VB is, right? And I know that that's the angle that VB has. Okay. I also have to add to this some rotation about point B. So I hold point B fixed, I rotate about it. I'm going to have some relative velocity at the tip, VD with respect to B. there's some angle in here that we need, and there's some angle here. How are we going to figure this angle, these angles out, right? It's going to be geometry also, right? So let's zoom in on that. And here's my velocity of D with respect to B. Here's the length. Right? This is BD. Remember, this is going to be perpendicular to BD, right? That velocity has to be perpendicular to the length at that point. This is going to get tricky to see. Right? Well, I know this angle in here, right? That's the one that we just found. That's beta. Yeah? Yeah, that's beta. Okay. What if I extend this line to there? Right? If I did that and I extend these things as such, we call this angle in here gamma, and this angle in here would be the complementary angle, right, which would also be gamma. Then how do we figure out what that third angle is? Well, the first thing we do is we have to figure out gamma, right? So I can figure out gamma. How am I going to figure out gamma? Well, right here, right? This is 90 degrees, right? Right in here. This is 90 degrees, yeah? Well, that means that 90 minus beta minus gamma, well, gamma plus beta is equal to 90. So 90 minus beta is equal to gamma, right? Okay, 90 minus beta, which is 13.95, is equal to gamma. So gamma is equal to 76.05 degrees. Right, so this is gamma. Okay. Well, hey, wait a sec. Wait a second. This angle right here is also 90 degrees, yeah? So gamma, 90 minus gamma has to give me back beta. Okay. So this angle is beta. We already calculated it. We'll just call this one beta. So we've got to do a little bit of geometry, right, to get that. But there we are. So now we know that angle, right? Great, very good. Call this one in here beta. Any other questions? Now that we have all of those things, we are ready to go, right? Because why? Remember what we need, right? We need to find the velocity of point P, the piston, right? And we also need to find the velocity or the angular velocity of the ball. So that's two things. If we have two things that we're looking for, we need two equations. How are we going to get two equations out of this? X and Y directions. How are we going to break this down? Well, we need those angles, right? If you don't have the angles, you can't make components in the X and Y direction. So let's write an equation. Right, remember, this is a big one. This is the important equation, right? I'll write it as the general format again. The velocity of some point on a rigid body, any point that you want, is equal to the velocity of some point that I know, right? I'm going to assume that that's A. In general, at some point A, I know A. Now, why don't we write it like this? The velocity of some random point is equal to the velocity of some point on there that I know. I know this velocity plus the velocity of the point that I want to know with respect to my known point. Okay. In this case, we know the velocity of B, and we want to find the velocity of D, right? So for us, right, so this is in general. This is the equation that you'll get on your equation sheet, right? For our specific problem, we want the velocity of point D. We know the velocity of point B. And we have V of D with respect to B. We can rewrite the equation again as V sub B, right, plus omega BD about the z-axis cross R of D with respect to B. And finally, I'll break this down as VB x in the I direction plus VBY in the J direction plus the cross product of omega BD K cross RD with respect to B. That's where we're at. So I know the velocity of B, and I know the angle that it takes place at, right? So I can break that into components. I can figure out VBX and VBY, which we'll do, right? We'll do that in a second. I can figure out R of D with respect to B, right? Because remember, that is just, if I'm standing at B, what vectors do I need to get to B, right? I'm sorry, if I'm at B, how do I get to D, right? If I'm at B, how do I get to D? And we'll talk about that in a second, too. And then we're going to have to solve the cross product and split it into two equations, right? So let's start with VBX, right? VBX. Let's go back. So right here. I want the x direction component of VB, and I know alpha. How do I get the x direction component of VB? Is it going to be a sine or a cosine? It's the sine or the cosine? The cosine. Exactly. That means that the y direction is what? The sine. Is the x direction positive or negative? Is my x velocity for point B positive or is it negative? Point B?
I guess that's the angular velocity thing.
Right, so remember, the negative angular velocity says that it's moving clockwise. That's what the negative sign there means. Right? For our velocity vector, we do everything based off of our x and y, right? And so it's moving to the right, it's moving in the positive direction. What about the y direction velocity? Is that going to be positive or negative? The y direction be positive or negative? To move it up or down? Be negative. It's moving downward. No. All right, this is moving down To the right, right? It's pointed down and to the right. Okay, so there's that. So we can figure that out, right? So we can come up with VBX. VBX should be V sub B cosine of 50 degrees. All right, what's that going to equal? 628.33 cosine of 50 degrees. Excuse me, 403.67 I meters per second, right? So meters per second in the I direction. Do the same thing for the Y, right? VB sine of 50 degrees is 628.33 sine 50 degrees. That's going to give me negative 481.33 in the J meters per second. All right, we're good on that, right? Everybody sees where that comes from. All right, you look at the triangle for the VB, give it the X and Y components, you know the angle with the horizontal, and so we can do that. All right, now we need R of D with respect to B. How do we find that, right? This is a mapping. This is, I am standing on point D and I need to get to point B, right? Bless you. I don't want to draw this. So you can break this down into components as well, right? I can go this way and then this way. Remember, we know this angle here, beta. I know the length of my hypotenuse, right? The length of this length is 8 inches. So I've got to go, if I want to go from D to point B, right? I've got to go negative 8 cosine of 13.95 in the X direction. And then once I'm at that point, I go 8 times sine 13.95 in the J. So R of D with respect to B gives me negative 8 cosine 13.95 in the I plus 8 sine 13.95 in the J, which would be 7.76 I minus 1.93. I messed up the sign. Oh, and I wrote meters per second. Jeez, that's not good. This is inches per second. My goodness, it's Friday. Inches are certainly not meters. Professor Higgins would scoff and beat me. Right? She'd hit me in the head with a rolled up magazine, rolled up ASME magazine. And all right. Turns out that I messed up my signs here, right? Because what did I tell you guys? All right, let's go back. R of D with respect to B, right? D with respect to B is how I go from B to D, right? From B to D. So the sines and cosines are the same. I just flipped my negative and my positive. Right, so I need to go negative J and positive I, right? My mistake, I apologize. This is correct. Right, so this, all the units are correct now, right? So we should be good to go, maybe, right? Let me see something. Good. Okay. Okay. We've got R of D with respect to B. We've got VBY and VBX, right? What is omega BD? Well, we don't know what exactly omega BD is, but I can write a vector for it, right? It's going to be 0I plus 0J plus omega BD in the K, right? This is only rotating about the Z axis, about the K, right? This is only rotating about the K. So that's going to be our, right? So I've got expressions for everything now, right? I've got expressions for everything. We can do our cross product. Okay. So the equation for VD is equal to 403.67 in the I minus 481.33 J plus IJK 0 omega BD. Remember, if you don't know which way something is pointing, right? Assume that it's positive. Assume that it's positive. So we're left with this. Okay. So if we're going to do our cross product, I don't know why I'm going to draw that again. I'm going to do my cross product. Cover up I. What am I left with? Yeah. If I cover up the I column, I've got J cross K, which is going to give me positive I. J, K. So what does my cross product tell me? What does my cross product tell me for my I term here? What do you guys think? What is the I tell me? We can do this. Somebody hit me with what the first part of the cross product is. We're covering up the first column in the top row. We're just left with that bottom corner there. We're left with that bottom corner. Left with this. What's the cross product in this corner? What do I get? negative 1.93 omega BD. Close, close to it. Very close, right? Remember, what is it, right? It's 0 minus negative 1.93 omega. So it's positive, right? Don't forget the negative, the extra negatives. What about the J column? Right? Remember, this is going to be I cross K. Right? So if I cover up the middle and here, right, I'm left with the corners, right? These four. What is my cross product for these four, the four corners? Zero minus 7.76 omega BG. But remember, this one's I cross K, right? So we have an extra negative here too. It's actually going to be positive when the math comes out. What about the last one? We cover up K, I cross J. What do we get? Zero. Right? Zero. So, we get something that looks like this, right? And we would expect to get zero in the K, right? Because this is a plane motion, right? There's no motion in and out of the page here, right? Everything happens in the X and Y direction. So it would make sense to us, hopefully, that we don't get anything coming in and out of the page. Okay, so we can, we'll rewrite this so it looks nice. And so this velocity vector is equal to this, right? But there's one thing we haven't talked about, right? The velocity of point D is a vector, right? It is a vector. So we need to talk about that. If that's a vector, we should be able to break it down into I and J components, right? And I'm going to tell you that it's VDI plus 0 in the J. Why is it VD in the I plus 0 in the J? Because remember what point D is. Right? Let's look at it. One more time. I want to go back. One more time. There we go. Point D is on the piston. Piston can only move horizontally, so will not have any vertical velocity, right? Point D is attached to this piston, so point D cannot move out of that housing, right? It is constrained to move in a line, so the velocity of point D is actually equal to the velocity of the piston, right? Because it is, point D is a point on the piston P, which is also a rigid body. So that's why we have 0J there. Okay. We can get there. Okay. So I'll rewrite my equation up here. I think I have a wrong sign in here though. There we go. There's no negative in there. All right, I think we're okay. We're good. All right, so I'm going to rewrite my equation up here so we have it, right, and it looks nice. We've got VDI plus 0J is equal to 403.67I plus 1.93 omega BDI minus 481.33J plus 7.76 omega BD. And we can break this down into I and J components, right? Because now we have we can get two equations with two unknowns. And if we do that, what will we get? Well, if we look at the I direction, right, we look at the X direction stuff, we get VD is equal to 403.67 plus 1.93 omega BD. And we get 0, right, if we look at the J direction now, sorry. In the J direction, we get 0 is equal to negative 481.33 plus 7.6 or 7.76 omega BD. I'm going to solve those. I'm going to solve this. Mm-hmm. Right.
Omega BD, actually,
Say that one more time, Zach.
omega BD, that's actually a variable.
Yes, that is the angular velocity of the length BD. So we can solve this, we can use it in our calculator, right? Or, you know, our favorite method. This one's not too bad, right? Because I can take this J equation, right? And I can say, well, 481.33 is equal to 7.76 omega BD, right? And so omega BD has to equal 62.03 radians per second, right? Which is what we're looking for, rather. I can then take this omega BD, right, and plug it in to my first equation there, right? And I'd get VD is equal to 403.67 plus 1.93 times 62.03. And that would give me Yep. 523.4 inches per second. Moving to the right. Man, that one was long, right? These are starting to chunk. These are starting to chunk a little bit. You guys have any questions on this one? There's another method that we can do, right? We could do this graphically if we wanted to. I'm hoping I've got one more slide up my sleeves here for that. Make sure to do that. Because remember, the book really likes to talk about these vector triangles, right? So we could do this using vector triangles as well, or velocity triangles, rather. Yeah, what the heck happened here? Excuse me. That's weird. Apparently, the solution happens before, yeah, I must have been a slot ahead or something. Weird. Well, that's fine. Okay, well, I'm going to use the bottom part of this to talk about what we just talked about. So I've got some velocity, right? I've got this velocity of point D, right? We know that has to be horizontal. I know that the velocity of B has to be this way. And because that's at a horizontal, this angle inside has to be 50 degrees, right? So I could figure out if I wanted V of D with respect to B, right? We know that this makes a 90-degree angle there, right? We can split this. Let's put this down here. I know the angle over here. We found this earlier. That was 76.05 degrees, right? Found that angle. If I know that angle and I know that this is 90 degrees in the middle, I can figure out what this one is, right? That tiny one. I also know that this is 90 degrees and I know that that's 50. So I can figure out this one and you can put those two together. And guess what? This total angle in here is 53.95, right? Because 90 minus 50 is 40, and we know the other one is beta, because 76.05. 90 minus 76.05 gives us that 13.95 back. So we're left with 53.95 for the rest. Great. It's another way that we could do it. Well, triangle has to have 180 degrees total, right? So 180 minus 76.5 minus 50 should give you back 53.15. But we can do this, right? And we can use law of sines again, right? So V sub D is equal to the sine of 53.95, which is equal to V sub B over the sine of 76.05 degrees, which is also equal to VD with respect to B sine of 76.05 degrees. Sorry, I have that written twice when I shouldn't. This should be 50. This one's for, let me try that one more time, guys. One more time. Friday. This Friday is killing me. I'm losing all my street cred this Friday. Okay. Turns out we know what VB is, right? We already figured that one out. That is 628.3. So I've got two things. I've got two equations here, right? I can figure out VD and I can figure out VD with respect to B based off of the ratio that we made with VB and the sine of 76.05. So if you solve both of these things, you get VD is equal to 523.45 inches per second, which is pretty close to what we got just a second ago. We know that VD with respect to B is equal to 495.96 inches per second. Well, V of D with respect to B is equal to the length of the bar times omega BD, and omega BD is equal to V of D with respect to B over L, which is 495.96 divided by 8 inches, which gives me 62.0 radians per second. So if you did this with the triangles, you're pretty close, right? What's the downside of doing it with the triangles? Is you got to do all the geometry to get the angles, right? Whatever you're more comfortable with, that's the best way to do it. All right, do you guys have any questions? Let me ask you a question. In the position shown, bar AB has an angular velocity of 4 radians per second clockwise. So bar AB is rotating this way, right? Going that way. Well, it says determine the angular velocity of bars BD and DE. But what I want to know is which of the following statements is true. You can tell me by showing your hands that the direction of VB is in the upward direction. Who thinks that A is true? Okay. Who thinks it's B? The direction of VD is to the right. And who thinks it's C? That both are correct.
Why is B wrong?
Why is B wrong? Because that's vertical at this instant in time. Because this is straight, both of these have to be up at this moment in time.
Okay.
Right? Just because at this instantaneously, at this snapshot, right? If this was slightly off, right? Remember, B and D, that's a rigid bar, right? So at this second in time, it has to be moving. If point B is moving straight up, B has to be moving straight up. If they were angled, then that'd be good. So we're going to talk about instantaneous center of rotation, like the guy did in the video. Right? So this is another method that we can use. And like in the video, what he said was, you can consider, so if we have our potato back again, right? I can draw the velocity of any point on that potato, but I can also relate it back to some point that is some distance away, that if I was standing there, it would just look like this potato was rotating about that. And that's the idea of this instantaneous center of rotation, right? The velocity of all the particles in the slab are the same as originally defined. It's angular velocity and translational velocity at A. So we're just saying, hey, everything, if you were standing here at this instant in time, it would look like a perfect rotation around you, right? And VA would tell you what to do, right, based off of that distance that you are away. As far as the velocities are concerned, the slab seems to be rotating about the center of rotation. All right, if the velocity of 2 points A and B are known, the instantaneous center of rotation lies at the intersection of the perpendiculars to the velocity vector, right? So on a potato, this doesn't seem like that big of a deal, right? But the example that the guy used in the video was our slider, and we're going to talk about our slider mechanism too, right? you're going to draw you're going to draw a perpendicular line to each of your velocity vectors. And wherever those intersect, that's where you're going to say that is point C. The guy in the video called it I. You can call it whatever you like, it doesn't matter, but that is my instantaneous center of rotation, right? So at that instant in time, it looks like everything is rotating about that point. If the velocity vectors are parallel, then the instantaneous center of rotation is at infinity, and the angular velocity is 0. Okay, so if you have two vectors that are the same length, if these are not, this is a little bit different case. If you have two that are the same length and they're parallel to one another, the perpendiculars will never cross. So there is no instantaneous center of rotation, right? Because if they don't intersect, then they can't change, right? Or then they can't have an instantaneous center, right? What happens if I have something that is, they're not the same size velocity, right? It's not the same velocity. VA and VB are different, but they're parallel. In that case, you can draw a line that's perpendicular and a line that crosses the tip of each of the vectors. And then where that converges, you have an instantaneous center here. Right? If the velocity magnitudes are equal, the instantaneous center of rotation is at infinity, and the angular velocity is. So here's our slider. Here's our slider again. The instantaneous center of rotation lies at the intersection of the perpendiculars, right? So hey, this is going straight down, perpendicular gets me here. This one comes up. Hey, that's where it intersects. Look, you can figure out what theta is. You have enough to use this triangle to figure out. And you use this triangle to figure out what your distances are, right? And then you can use that to figure out either omega or one of your velocities. Omega is equal to VA over AC. VB is equal to VB BC times omega. The velocities of all the particles on the rod are as if they were rotated about points. The particle at the center of rotation has 0 velocity. So if you're standing here, this point at that instant in time is a stationary point. And so in this snapshot, at this instant, if I'm standing on C, C will not move, but everything's moving around C. Okay? The particle coinciding with the center of rotation changes with time, and the acceleration of the particle at the instantaneous center of rotation is not. So, you kind of saw this in the video. The guy moved it, and you saw that C or I moves with time, right? So as this slides out and this slides down, the position of C in space changes, right? So we follow the line like this, or a line like this, okay? The acceleration of the particles in the slab cannot be determined as if the slab were simply rotating about C. So this only helps us find velocities. It will not help us find accelerations. And the trace of the locus of the center of rotation on the body is the body centroid, and space is the space centroid. So wherever this point C goes, if you plot it for all time for your system, if it's in space, we call this the space centroid, and if it crosses onto the body that we're talking about, then it is a body centroid. Okay. Those are two terms that we will never, ever talk about ever again. So there's that. Okay. So at the instant shown, what is the approximate direction of the velocity of point G at the center of my goal? So at this instance shown, what is the velocity? What's the direction, right? Who thinks it's to the right? Okay. Who thinks it's up and to the right? Thinks it's down and to the right. Okay. Who thinks it's just down? It's down and to the right, right? How are we supposed to know that? Well, there's two ways you can think about this, right? The first one is this is moving and this is moving. One's moving down and one's moving to the right. So the entire motion of the system should be down and to the right, right? We're going to combine those two vectors. The effects of those two vectors will give me a motion down and to the right. But if we're using the instantaneous center and we're saying that everything rotates about the center, then this velocity vector has to be tangential to the line from C to G, right? So it has to be down and to the right. So we're going to do this problem again, right? But this time, we're going to use the instantaneous center method, right? And see if we get the same answer. So I'm going to skip the first part of this problem because we did it last time and it doesn't change, right? We need to find VB, right? And remember, VB that we found earlier was 628.33 radians per second down at 50 degrees. All right, so let's just start with a diagram of the connecting rod. I'm going to do that way down here to give myself enough room. Here's B, here's D. Here's VB. Remember, VB has an angle of 50 degrees from the horizontal. We also have the velocity of point D. This angle down here, we found before, that was our 13.95 degrees. So I need to draw a perpendicular from each of these, right? Well, this one's an easy one to draw, right? We'll just draw a perpendicular line, right? Straight up from there. Good. This one, if we're at 90 degrees to that, it's going to be somewhere around here. These two things coincide here. I call that C. All right. I know that this angle has to be 40 degrees. There's two reasons why I know that angle has to be 40 degrees. First of all, this line is perpendicular to my velocity vector, right? And I know the angle here from horizontal is 50 degrees, so the rest of it has to add up to 90. The second way that I know that is from the first time we did the problem, we calculated it already, and we know that it's 40 degrees, because if it's perpendicular to B sub B, then it has to be at the same angle that AB is, right? So we can figure out, we need to figure out another couple angles. I'm going to need to know this one in here. And I'm going to need to know this one here. I'm going to call this one right here gamma and this one delta. And I'm going to say that this angle is 50 degrees. Why am I going to say that that one's 50 degrees? Good question. Well, I know that this has to be 40 degrees, right? Because it's the complementary angle to the other one. This angle is 90 degrees. All right, so 180 minus 90 minus 40 gets me 50. So how do I find gamma and delta? Well, gamma is not too bad. We actually found gamma earlier today already, right? Gamma is just 90 degrees minus 13.95, which is my 76.05 degrees. What about delta? How do I find delta? Well, delta is going to be 40 degrees plus 13.95 degrees, which gives me 53.95 degrees. How did he do that? This angle in here has to be 13.95 degrees, right? It's the same as the angle right here. Okay. This angle at the top from the horizontal is the same as the angle from the horizontal to here, right? So we've got all of our angles, right? Now we can use law of sines and law of cosines to figure this out. I'm going to call this length BC, and I'm going to call this length CD, and we know already from the problem statement that this length was 8 inches. Right? We were told that that crossbar was 8 inches. So by law of sines, BC over sine of 76.05 degrees is equal to CD over the sine of 53.95 degrees is equal to 8 over the sine of 50 degrees. I can solve for BC, and I'll get 10.14 inches. I can solve for CD, I get 8.44 inches. So what do we do from here? Well, I can determine, I know VD, right? And I know the distance that it is away from C. So I should be able to come up with an expression for omega BD using that, right? Because VB is equal to BC times omega BD, right? I know BC, I know V sub B. So omega BD is equal to 628.3 divided by 10.14. Guess what, guys? That's 62 radians per second. It's basically exactly the same as what we got when we did this the first time. Can we do the same thing for VD? Sure. So this time I know what omega is, right? So this just becomes a direct solve. And this is roughly we got last time too, right? Then we get like 523.24, something like that. Yeah, I could look. It's like one page. I could listen to me. Yeah, 523.4. Sorry, that's not too. We're off a little bit. Pretty close. Can you use this all the time? Right? This is certainly a lot simpler and a lot nicer, right? No, you can't use this all the time. Right? You can't use this all the time. When can we use it? You can use it when we're talking about velocities, right? We use it to find velocities. We can use it as long as our velocity vectors aren't perpendicular, right? As long as you can draw Sorry, as long as our velocity vectors aren't parallel. As long as you can draw a perpendicular line from your velocity vector that intersects with the perpendicular line from the other velocity vector, you can do this. But it will only get you information about the velocities, right? It will not get you information about the acceleration. Okay? Don't try to do this for acceleration anymore. All right?
They compare all high school with, you only know that angle and two sides are, I don't know, of course, connected. The triangle.
So you could use law of cosines if you know. So it depends. It depends on what you know, right? If you're gonna end up doing a problem like this, you need to know certain things, right? You're gonna need to know at least one side and all of the angles, right? To do this. Or if you knew the lengths, but you didn't know, you knew all the lengths and only one angle, right? That will work too, or some combination thereof. But we need to know something. Yeah, you're right. There does exist conditions where you cannot use law of sines or law of cosines to get things done. You guys have any other questions? No? Pretty quiet today. It's pretty quiet everywhere. All right, what happens to the location of the instantaneous center of the velocity if the crankshaft angular velocity increases from 2,000 to 3,000 RPM? What if this starts to spin faster? What happens to the instantaneous center? Does anything happen to the instantaneous? How do we find the instantaneous center? Yeah, Julian. Yeah. Right. If we're looking at it at the same moment in time, right? If we're looking at it at the same moment in time, doesn't matter how fast it's spinning, the instantaneous center will still be where it's going to be. Right? The only thing that's going to change it is if we change our orientation. So what happens if I change the orientation? And beta is now 0 degrees. So essentially, right, what does beta being 0 mean? I've got this flat. Right, remember, this is still going to go here. What does V sub B look like if this is flat? And how does that change my instantaneous center? Yeah, Julian. So yeah, VB, right? You said VB coming down vertical, right? So if you were to draw perpendiculars to this, where would they intersect? Right there. This is actually going to be a point D, right? It's going to be somewhere on the bar. Now think about it, right? If this is flat, what does this mean for where the piston is, right? This means that the piston is basically all the way, like it's going to be all the way compressed or all the way extended, right? One or the other. And so it's going to be like that's a fixed point. The velocity is basically going to be 0, right? And so that's going to be like it's fixed and everything's rotating around that point, that instant in time. Okay. Yeah, cool. You guys have any questions on instantaneous center? Because we're gonna get a little bit into how we handle acceleration. And it's a very similar process, except there's no fun, well, not fun, but there's no instantaneous center method that we can use, right? We're going to have to use relative and absolute acceleration, right? So the human-powered vehicle, which we actually have a project at GCU, the ASME club is working on a human-powered vehicle. Bicycle, as it accelerates, a point at the top of the wheel will have acceleration due to the acceleration of the axle, right, or the linear motion of the bike, but also tangential acceleration of the wheel from the angular acceleration and a normal acceleration due to the angular velocity, right? So some of these, as we start to accelerate, things change for us, right? How so? Well, remember, in general plane motion, what we're doing is we're still going to treat this as a combination of a translation and a rotation. But because this is rotating, now we need to deal with normal and tangential acceleration components, right? So what do I mean? If you look at this, right? I've got the acceleration of A, I've got the acceleration of B, and the acceleration of B with respect to A. But I can break this down into normal and tangential components, which are both perpendicular to each other, right? So this is just making a right triangle. And where does this come from, right? Well, this comes from when we were doing kinematics, when we're talking about normal and tangential coordinates. Why are we using normal and tangential components here? Because it's a rigid body, there's a set amount of rotation, right? So remember what I'm doing here. I'm holding this point fixed, and then I'm rotating around it, right? So there is a set radius of rotation that I'm spinning around, right? That radius isn't going to change. It's going to stay constant, and it's going to rotate about that point, right? If I hold this constant here and I start rotating it, right? This distance remains constant the entire time, right? Likewise, this distance from A to B is going to be constant the whole time, which is why we use normal and tangential coordinates to talk about this. In that regard, remember that our normal acceleration will always point back towards the center of rotation, and our tangential acceleration will always be tangential to the path. Tangential acceleration is going to be due to our angular acceleration in the same way that our tangential velocity was due to our angular velocity. And our normal acceleration is actually a function of our angular velocity. Okay. So let's use our crank and slider here again, right? So given the acceleration of point A, and the velocity of A, I need to determine the acceleration of B and alpha. Some of these get a little bit more complicated, and we'll talk about why in a second. I can write out my equation, right? AB is equal to AA plus AB with respect to A, right? These relative acceleration and velocity equations will be provided, right? But remember, this stems from AB with respect to A is equal to AB minus A. Right? That's how we defined this a few weeks ago. Cool. I can break down A of B with respect to A into normal and tangential components, which is what's happening here. Right? The vector result depends on the sense of A and the relative magnitudes of A and A of B with respect to A in the normal direction. And we also need to know what omega is. Okay, so there's a bunch of different vector combinations drawn here on the screen, right? What do they mean and why do we care? Well, it turns out that there exists a case where the acceleration of B is both can either be up or down in both cases. In that position, the acceleration of B could be going upward or it could be going down. And we don't know. But we know what A sub A is doing, right? So we're going to assume everything's accelerating by the acceleration of A. But in the same regard, when I hold this fixed, I can either be in this position, speeding up, right, which would be the acceleration going in the same direction as my velocity, or it could be slowing down, right? Again, because you could be moving upward or downward, right? You have all of these different combinations. And that's what these are showing, the different possible permutations of the acceleration. So how do we pick? How do we pick? We just pick one, and then you stay constant with it the entire problem, right? So you say, I'm going to solve this problem as if A is moving right and AB is moving down, right? And that's how you do it. And then if it comes out differently, if you get negative signs, that means you chose wrong, right? You get a negative sign, it means you chose the wrong direction. Okay? So just like everything else, we assume it's positive, right? We assume the positive sense. If it comes out negative, we know we chose wrong, and we have to pick it the other way. Okay? But there is a little bit of variability in what you can choose and how you can choose. So, in most cases, for the problems that we do, it should be fairly obvious which way things are moving. Should be fairly obvious. All right, so we can do this again, right? This time we're doing it. Well, right, so here, which one are we picking? We're picking case A. I'm assuming things are moving down and to the right, and so I can break down this into my normal and tangential components, right? A and B with respect to A. And so here, I'll write out my x components for this, because I know the angles. I end up with 0 is equal to A sub A plus L omega squared sine theta minus L alpha cosine theta, right? And then I can write a y component equation. Negative AB is equal to negative L omega squared cosine theta minus L alpha sine theta. And I can solve these two equations for A sub B and L. So the acceleration equations, just like the velocity equations, are typically going to boil down to us needing to solve a system of equations. Right? Sometimes it's helpful or advantageous to figure out what the absolute velocity and acceleration of the mechanism is directly. So in certain cases, much like this one, what happens? Well, I know this length at this time. And I know this one. I know x sub A and I know y sub B. X sub A is L sine theta. Well, I want the velocity. I take the derivative with respect to time. If I do that, I get L omega cosine theta. If I take the derivative again, I'll end up with negative L omega squared sine theta plus L alpha cosine theta, which is what we got before. Right? Same deal. I come here and do it for my y, right? I know y is L cosine theta. Take the derivative once, get negative L omega sine theta, and I take it a second time, and I get negative L omega squared cosine theta minus L alpha sine theta. Okay, this works if you 100% know what XA and YB are, and it's a right triangle, right? If it's not a right triangle, then you have to figure out all the angles, right? And you can't just write it as a nice sine theta, right? So sometimes this doesn't play, right? But when it does, you can see how this is a lot simpler than trying to use relative accelerations and velocity, Is there any questions so far on this? So what's the big ideas here? The big idea is really this. This is going to be, we need these, right? We need this for AB with respect to A, tangential, and AB with respect to A normal. These are really important, right? So if we are going to be doing a problem where we need to find the acceleration of something, or alpha, you're going to need the angular velocity. So essentially, whenever we do one of these problems, right, you're still going to need to solve potentially for omega if you're not given. Well, how do we do that? That's the whole thing that we just did, right, with the velocity equations. You can get omega in certain cases using the instantaneous center, right? So you don't need to kill yourself all the time to get all these things, right? What else would we need? Well, we need alpha. How do we get alpha? Well, you need to solve for alpha in A sub B. If you just calculate omega, that's the only thing that you really don't know in that equation, right? All right. So, congratulations, by the way. You've made it to the kickball championship game. Great success. As you try to kick home the winning run, your mind naturally drifts towards dynamics, as is typical for all higher level athletes. Right? I mean, when you guys watch any sport, right? Like you watch football. Patrick Mahomes is doing all of these projectile motion equations in his head on the fly, right, while under pressure. Really high level, right? Okay. Which of the following thoughts is true and causes you to shank the ball horribly straight to the pitcher? A, energy will not be conserved when I kick this ball. B, in general, the linear acceleration of my knee is equal to the linear acceleration of my foot. C, throughout the kick, my foot will only have tangential acceleration. Or D, in general, the angular velocity of the upper leg, or thigh, as sometimes people call it, will be the same as the angular velocity of the lower leg, or the calf. All right, so who thinks it's A? Who thinks that energy will not be conserved when you kick the ball? Who thinks it's secret answer E? What does this have to do with anything that we've just been talking about? It's a good question. Who thinks it's B? In general, the linear acceleration of my knee is equal to the linear acceleration of my foot. Who thinks that throughout the kick, my foot will have only tangential acceleration? It's D. In general, the angular velocity of the thigh will be the same as the lower leg. It's actually A. Energy will not be conserved when you kick the ball. There's friction, and the ball makes that nice kickball sound when you kick it. I can't make it right because I'm not a kickball, but you know the sound, right? Especially. Yeah, it's true. We do. But it's a collision, right? Collision we typically do with momentum and influence. Well, that's true. All right, so fair. That is a fair point, Zach. I will give that to you because energy is conserved. We know that. It's just that mechanical energy will not be conserved, right? Mechanical. So fair point. It's not a good question. I have to revise it. All right. Do we have time? No, we don't have time. We'll do this next class. Hey, look, it's that same problem again. What are we going to be doing this time? Hey, we're going to be finding the angular acceleration and the acceleration of point D. Does this mean that everything we just did on it previously goes out the window? No, it's actually really nice that we did that because we already have stuff solved, so we don't have to step through everything to get where we're going, right? But we'll review some of the things from this classroom. Right? So next class, we will talk about this problem, and then we're going to jump in next week ooh, to rotating frames. Rotating frames are, you'll see. Rotating frames are tricky. They're in the sense that they're tricky in the sense that when you're trying to visualize them, sometimes it gets hard. But I have a video that will hopefully help us do that. Okay, and so here we are. We're done. Have a great weekend. Do something. Play Fall Guys, whatever it is you guys do. Coming to class. So great job, everybody in the room. If you're watching this and you didn't come to class, you know who you are. You know who you are. You should come to class. What's up? I don't know. Not right now. So here's, I said it during the last class, I'll say it again. Next week on Friday, our participation will happen, right? Dress in your Halloween costume, or if you don't have a Halloween costume, just be Halloween festive, okay? Be Halloween festive in some way. Yes. I did it. It was really creepy. My first year here, I had 2 students come in late dressed as the Joker and Batman, and that was like, it was like a really realistic Joker mask, like for 7 a.m. It was hope they didn't drive here in it, but you know, that's, yeah. And then at the end of class, we'll have some mandatory fun, which is the best kind because you have to have it. So. Okay. Yep.
I don't think I'm gonna be here Wednesday either, because I'm probably going home soon.
Okay.
So I'll just.
All right, well, make sure you do notes, and then I'm gonna give you an article to read for participation that you put the comments on. Okay? Cool. Sounds good. Let me know if you're not gonna be here for sure on Wednesday. Just shoot me a private message. All right? Cool. Sounds good.
So I think as a PowerPoint. Those
Easy.
questions are,